The fundamental theorem of calculus tells us that if you start with some function f that is continuous, and you build an area function out of it, what you get is an antiderivative for the original function, little f. And that's nice, but we have other ways of getting antiderivatives. If you remember back from Calc 1, we were able to guess antiderivatives a lot of the time. So, the area function is one antiderivative, but you could have also just guessed an antiderivative. So here we have multiple antiderivatives for the single function, little f. And I've sort of used the traditional notational device of calling an antiderivative the capital version of the function that we started with. So we have these two antiderivatives for little f. I guess I would like to know in this situation, what is the relationship between these? There must be a relationship. And in Calc 1, you probably discussed this relationship. If you have two antiderivatives for a single function, they always differ by a constant. So that means that a of x must be equal to capital F of x plus some constant that we don't know yet. Right? We don't know what this constant is, but there must be some constant we can add to capital F that gives us capital A. And this is because they're both, capital A and capital F are both antiderivatives of little f. So sort of the slogan version of this is two antiderivatives differ by a constant. Right? And that's what we have written down here. So I guess what we should do now is try to figure out, is it possible to know what constant this is? Well, for any area function, are there any x values we could plug into this area function that we know something about? For most x values, the answer is no. If we plug in 1 into this area function, what do we get? Who knows? We don't know what little f is. There's no way of telling what we get if we put 1 in here for little x. What if we put in 2? Who knows, right? The only x value where we know a value of this area function is if we plug in little a. So let's plug little a into here. So if we plug little a into the left-hand side of this equation, we have to plug it into the right as well. So the right-hand side of this equation becomes capital F of little a plus a constant. Well, I said we know what the area function is at little a. What is it? Well, remember the area function is the integral from little a up to your input of f of t dt. Right-hand side is still capital F of a plus c. But we're putting little a into this function, so we have to put little a right here. But what is the integral from little a to little a of f of t dt? It's 0. And now we have an equation. 0 equals capital F of little a plus c. And we can use this equation to find this unknown constant c. Just move it over. C is negative f of a. And this is really nice because this tells us that capital A of x is capital F of x minus capital F of little a. Now this probably doesn't look so amazing, but let's imagine that we were trying to calculate a definite integral like this. The integral from little a to little b of little f, like this. Well, look, this is almost the area function. In fact, it is the area function, but it's been evaluated at b. So let's plug in b into this equation. So if we plug b into this equation, the left-hand side becomes little a of b. The right-hand side is capital F of b minus capital F of a. So the right-hand side is capital F of b minus capital F of a. And the left-hand side is, well, it's this integral, the definite integral from a to b of f of t dt. So this is sort of another version of the fundamental theorem of calculus. And this gives us a way to evaluate definite integrals. It says that all you have to do is, step 1 to evaluating a definite integral, guess an antiderivative. We have so much experience calculating derivatives that a lot of the time we can just correctly guess an antiderivative. So guess an antiderivative, capital F. And then step 2 to evaluating a definite integral is plug in your bounds and subtract. That is all we will have to do to calculate definite integrals. Guess an antiderivative, and then plug in your bounds and subtract. That is much, much, much easier than calculating the limit of a Riemann sum. So this version of the fundamental theorem of calculus is a great, great tool for calculating definite integrals. The only caveat it has is that our integrand function, little f, has to be continuous, so must be continuous on the interval from a to b. If your integrand is ever not continuous, you have to be careful, but most functions are continuous in most places. So in practice, this version of the fundamental theorem of calculus will let us evaluate most definite integrals.